In our recent lessons, we've been thinking about nuclear decay. And most recently, we thought about half-life, which is the amount of time it takes for half of a radioactive sample to decay. Because every element has a different characteristic half-life, we can actually use that to date things. We can think about how long ago in the past something happened by how much of it has decayed. Specifically, we often use carbon-14 as an isotope to date things. In this lesson, we're going to learn just how carbon-14 dating works. Let's take a look. So here we have diamond. You can notice there's this diamond here and this chunk of rock. So somebody's mined a diamond out of the earth. And it turns out diamonds are made of carbon, which is kind of surprising, but the diamonds that we have are made of just carbon. And if you take a close look at the carbon in diamonds, they come in two versions. There's carbon-13, that is carbon with 13 things in the nucleus. And there's carbon-12, that is carbon with just 12 things in the nucleus. So these are the same element, carbon, but they're different versions. Remember, we call that an isotope. 99% of the carbon in a diamond is carbon-12. Just 1% is carbon-13. So almost all of it is carbon-12. But notice there's no carbon-14. That's interesting. So where does carbon-14 come in? Well, there's no carbon-14 in diamonds, but actually in the atmosphere, there is carbon-14. So here's what happens in the upper atmosphere. The sun rains down cosmic rays. Those cosmic rays are neutrons, and that's what we have shown right here. That neutron can then strike gases in the atmosphere, including nitrogen. So a neutron comes in and strikes nitrogen-14. When that happens, we combine nitrogen-14 with a neutron, and then that turns out to form carbon-14, and it leaves behind a hydrogen. So this is how carbon-14 is formed in the upper atmosphere. It's formed by a cosmic ray striking nitrogen and then undergoing a nuclear reaction. What that means is we have just a little bit of carbon-14 in the atmosphere. So 14 things in the nucleus now. Notice it says just trace amounts. So most of the carbon in the atmosphere is still carbon-13 and carbon-12, with almost all of it being carbon-12. But there's just a little bit of carbon-14. And that's really important when it comes time to try to use carbon-14 to date things. Because it turns out this carbon-14 goes and enters into living organisms. How does that work? Plants absorb carbon-14 in the form of carbon dioxide. So after that carbon-14 is formed, all three of these different carbons are absorbed into plants in the form of CO2. So you might remember from biology class, say, that plants undergo photosynthesis. That is, they take in carbon dioxide and light and water, and they use that to make sugar. So all of the time, plants are taking in carbon from the atmosphere. And then here's the thing. Guess what happens? Those plants now have trace amounts of carbon-14 in them, and then other organisms, like cows, come along and eat the grass or they eat the trees, and they also then get trace amounts of carbon-14. By the way, then we come along and we eat cows or we eat trees. I don't know if we eat trees, maybe the fruit off of trees. Anyway, we get trace amounts of carbon-14 in our bodies as well. So all living things have a certain particular ratio of carbon-14 to carbon-12. And that's what we see stated right here. So if you compare how much carbon-14 there is to how much carbon-12 there is in living organisms, that stays the same because we're constantly eating plants and animals that have brought in carbon from photosynthesis. Okay, how does this process proceed from here? We now know that all living organisms have some carbon-14 in them. Well, here's the thing, is that once an organism dies, that carbon-14 begins to decay. So the reason that diamonds don't have any carbon-14 in them is because they're made of organic matter that's so old that all of that carbon-14 has decayed. So once an organism dies, whether it's a plant or an animal, the carbon-14 starts to decay and eventually lose their carbon-14, and that takes time. So here's how that carbon-14 decays. It undergoes beta decay. This is actually a beta decay reaction we looked at in our beta decay video. Here's carbon-14. There's our beta particle. When that beta particle comes out, we get back our nitrogen-14. And this decay process is happening all the time in your own body. and in that cow's body and in that tree's organic material, always undergoing these decay reactions. Okay, well, how often do these decay reactions occur? Well, in living organisms, which have a fixed amount of carbon-14 per carbon-12, each gram of carbon will undergo 13.6 decay reactions every minute. And so if we take what's called a Geiger counter and we pass it over by this cow here, or we pass it over by the tree, the Geiger counters click every single time they hear decay, and it'll click, 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 click. And what it's measuring is those beta particles coming out of that material. And living organisms decay at a certain rate, and once they die, that decay rate starts to drop. Why is that? Well, when we think about carbon-14 and the half-life, carbon is constantly decaying into nitrogen. So let's say at time 0, when the organism is alive, there's 10 grams of carbon. Okay? So this is a pretty small organism, apparently. Maybe it's a grasshopper. And then after one entire half-life, well, there's half as much carbon. So that would half however many decays there are, because the decay rate was per gram, remember? So this was 13.6 decays per every gram. So that means originally it was undergoing about 130 decays every minute. Okay, and then once it degrades, once it's undergone a bunch of decays, and now there's only 5 grams, it's only going to be undergoing about half of that decay, or about 65 decays per minute. Now, how long is that half-life? It's 5,700 years. So it takes 5,700 years to go from 130 decays to 65 decays for this sample of carbon. And so what we can do is we can compare living organisms' decay rate to organisms that have died and their decay rate. And then we can, by comparing those, figure out how old they are. So let's take a look at a specific example. If you look at living organisms, living plants, say this tree, 13.6 decay reactions per minute per gram, like we've said. Now let's say we come across a really old text. That turns out to be called the Dead Sea Scrolls. It's a collection of writings which include the Old Testament of the Bible that were written by the Dead Sea long ago. And you might want to know, okay, well, when were they written? Well, what you can do is you can take a Geiger counter and you can measure how many decay reactions they're undergoing. Turns out they're undergoing 10.6 decay reactions per minute. Okay? And so now that I've measured both of those decay reactions, all I need to do is to compare them with a little bit of math, and I can figure out how old the Dead Sea Scrolls are. Let's practice that. Okay, if I want to do that, here's the math I got to go through. This equation compares the initial rate and the final rate. So rate 1 is that rate at the beginning when the organism is alive. So whatever plants were used to make the Dead Sea Scrolls originally were undergoing about 13.6 decay reactions every minute per gram. And then we compare that to the final rate, that's the rate we measure today. And then we need to also take into account the half-life. So the longer the half-life, then the longer it takes for the decay rate to drop. So the half-life goes in right here, which remember we saw for carbon-14 was about 5,700 years. This ln is what's called the natural log. You'll find that on your calculator. If you have a scientific calculator, hunt around for ln. If you can't find it, by the way, you can go on Google and you can say, where's the natural log button on, and then type in the model number of your calculator, and it will help you find it. So when you use this equation, you have to type in ln on your calculator and then plug in R1 and divide by R2. Okay, so that's how we can calculate the age, how old things are. Now, importantly, we're assuming that the rate of decay that we measure today is similar to what it was in the past, which means things like the amount of carbon-14 in the atmosphere are constant. And so there's actually a fair bit of more details here that have to go into this to think carefully through the process of carbon-14 dating. But this is a picture that we can take to understand how the process basically works. Okay, let's actually calculate the age then of the Dead Sea Scrolls. All right, well, the Dead Sea Scrolls have a decay rate of 10.6 decays per gram per minute. How old are the Dead Sea Scrolls? All right, well, all I got to do is write down my formula, age equals, and now I'm going to put the half-life of carbon up top, 5,730. Notice all I'm doing is copying this formula over here. I know age is equal to half-life, and so now I'm going to divide. What am I going to divide by? 0.693. And then I know I'm taking the natural log. By the way, this is a multiplication. And then the open parentheses means we're taking the natural log of rate 1 over rate 2. So rate 1, we know, is 13.6 decays per gram per minute. And the decay now, we're told in the problem, is 10.6 decays. 10.6. Okay, when we take that and plug it into our calculator, we want to do 5,730 divided by 0.693 times the natural log, open parentheses, 13.6 divided by 10.6, close parentheses, and we click enter. Okay, so definitely grab your calculator and do that with me. When we do that, we get out an age of 2,060 years. Okay, so pretty old. That means that the Dead Sea Scrolls were copied in about 50 BC. Okay, so a long, long time ago is when these scrolls were written down. And you can imagine that archaeologists love to use carbon-14 dating to try to pin down when things happened in history. So that's how we can use the tools of chemistry to figure out how old something is. Hey, hey.